1000K and software principles. So with that, we'll do the experiments. So the first and actually in electronics laboratory, then this is the first analog experiment, which will be based on the Wheatstone bridge with a low pass filter. So everybody has tried doing the experiment once.
Yes, ma'am.
So
Yes, ma'am.
So do you need me to give a brief of the experiment, or you have understood the experiment and we should go directly for the doubt clearing part? So you people do need to. Okay, okay. So I will go through once in a brief of the experiment, and I'll share the screen with you. And just a minute. Is the screen visible to you?
Yes, ma'am.
Okay. Great. So the first is this is a Wheatstone bridge experiment with a low pass filter. So you have an idea of what is a Wheatstone bridge, how it works, why is it, what is the requirement of using a Wheatstone bridge, and how it connecting a capacitor on any we can use it as also a low pass filter. So you'll have a brief idea of the working principle of our Wheatstone bridge circuit. So first of all, these are the materials and equipments that are already provided to you, and hope everyone has received the equipments and materials required for doing the experiment. So there will be four. I think everyone has received. Yes, right?
Yes, ma'am.
Yeah.
Yes, ma'am.
So we'll move to the first part. This experiment contains three parts. Uh, so the first part will be the balance, how to make a balanced Western bridge using referring figure 1. So this is there will be R1, R2, R3, R4. So all the values of the first of all, you have to measure the actual resistance of the uh, resistance values of R1, R2, R3, R4, because whatever the values written in the given that it is 100 kilo ohm resistors, in reality it not be the same because of the manufacturing defects like that. So you have to measure the values, actual resistance values of the resistances that you will be using in the um, experiment. So then after that, after confirming what are the actual values and what are the theoretical values, so you will have a idea of what are the difference in the resistance values. Then you will construct a Wheatstone bridge with excitation 2.5 volt DC from the analog board to the top arms of R1 and R3. Just refer figure 1 like that. Okay. And again, I will connect the ground to this. So here the ground is not present, there will be a ground. Okay. So connect the ground in this point, a node B and node R2 and R4, right? So after that, you will measure the voltages individually at node A and node B, and the output voltage V0 between node A and node B. That means what? That means the output voltage, that is VA, you have to measure. So individually we'll measure the voltage VA, note it down, measure the voltage VB, note it down, and also uh, make a table of what is a critical values. You can show those things in the video that we'll be making while doing the experiment. So you'll have a table or have a written up that write up that these are the theoretical values, expected theoretical values, and these are the experimental or measured values that you are getting. So there will be some differences. So you will infer what are the reasons of those differences in the between the experimental values and the theoretical values. So and then after that measure and record the voltages. Then user mana record the output voltage. So like that, measure and record the voltages. Node A, node B, node that VAB with using the multimeter. Okay. Record the output voltage. It should be close to zero, as because the bridge is balanced, because R1, R2, R3, R4 are similar values. But then also there will be some variations which you have to attribute some factors, so that you can explain in the video. Now you have to repeat the same thing, keeping R1, R2, R3, R4 as constant, as same as before, but changing the excitation voltage, that is E in figure 1, as 2.5 plus 1 sine omega t. That you will add a AC source as well, so that you can get it from the ADLM kit. You can make that. Then that also might you will also see that it will give a balanced bridge or not. That you have to understand. Hopefully it will give. So if the components available are 1 kilo, now the seven point is that you will the components available are only, before it was 100 kilo ohm, R1, R2, R3, R4. Now if you have a components as 1 kilo ohm, 100 kilo ohm, 1 and 10 kilo ohm, how will you put the resistances in which resistance, R1 as what, R2 as what, and make the bridge balanced. So that you have to figure it out and check the same with 2.5 volt and AC, with DC excitation and both as AC excitation as well in this case also, and check how the uh, node voltages and the V output V naught changes. Part 2 of the experiment is add 1 kilo ohm resistor in series with R1 and another 1 kilo ohm resistor in series with R4, and calculate the node voltages and output voltages V naught between VA and VB. So now the bridge will, this is a not in balanced condition. Now the Western bridge will not be in a balanced condition, and check the node voltages and output voltages. Measure and record the voltages that you are getting in the multimeter. Record them and compare it with part 1, and you have to write the inferences. What if there is a change in the output voltage that you are getting, what is the reason for the difference in the output voltages. The third part is low pass filtering. So here you will retain the 1k resistors introduced in part 2, in part 2. Then you will add a capacitor and across VA and VB, across that. Now, using you'll there will be a VAB, but you will after connecting the capacitor, after adding the capacitor to the circuit, you will face a you will see a low pass filtering effect. Now, in with your ADLM kit, you might face some challenges that you will figure it out while doing the experiments. If anybody has done the experiment, or whoever has done the experiment, that they will be able to understand, and they will able to see there will be some problems you will face that I will not mention now. Uh, Maybe you can infer it in your video, and why you are facing this problem, what might be the reason for this problems that you are facing while measuring the VAB, or to see the filtering effect while adding a capacitor across VAB. Here you will connect a capacitor. Now, lastly, you have to now you will also check. Now you have to how you will see, you will just change the frequency and check how the voltage, that is a V out, changes when you switch the frequency. The RMS voltage actually measure the RMS value of the same using the oscilloscope available with the analog port. Now you will face some problem. You will infer that in your video. What is the reason for that issue? You can inform us in the video, and then you will make a you can make a circuit using the Thevenin, represent the circuit, represent the figure 1 as using the Thevenin equivalent circuit across node A and B. And again, you connect a capacitor as the load for that Thevenin equivalent circuit. And again, you will give E as a this excitation and change the frequency, sweep the frequency from, I think it is from 1 hertz to 1 kilohertz, and see the changes, how the V out will change. So the Thevenin equivalent circuit is an equivalent circuit to the Western bridge circuit. So that will give you an idea of how if you connect a capacitor, how the low pass filtering effects will be there, and what will be the, and you have to also theoretically measure the corner frequency, and also from the graph you will plot the graph frequency versus V output graph. When you sweep the frequency, you will have a the V out will, the RMS voltage will change, and that you have to plot, and from there you will have to also figure out the corner frequency. So and then compare with the theoretical value and the experimental value. That is the brief of your experiment. So that's it. So any questions, any doubts?
This Beatstone bridge I have seen in one IIT Madras NPTEL video. Do I
Yes.
have to watch any video in order to do this thing?
No, I don't think this is a simple circuit. You don't have to, if you want for your knowledge, you can obviously go through any number of videos, but you don't have to see any particular videos. Everything is written here. You just have to go through the steps and do the experiment. For your knowledge, you can always refer to some videos, any books, anything.
Okay.
Any questions? Any other? Any other questions you have?
So, what is the value of the capacitance that has been provided in the kit?
No, not from the kit. I think materials required it is given. Now, capacitor in the nano range. So whatever the capacitors you have received, that you can use. I am not absolutely sure about what the capacitor values you have received. So you can preferably in the nano range.
In the part 3, we have to calculate the cutoff frequency.
Yes, yes,
So
yes.
for that, should we just take capacitor as 1 NF because we cannot measure the capacitance? So can we just assume that it is 1 nanofarad?
Yes, you can. In the multimeter, it is not there, no?
No,
Yeah,
multimeter,
yeah.
the capacitance
Value
measurement is not there.
not be there. Yeah, you can whatever the value you are getting, that in the kit, whatever capacitance value it is written, you can take that and do the experiment. We just need to see the plot, and how you actually, for you guys to understand how, what is the effect of attaching a capacitance to the load, so that how the low pass filtering will be there, and by after you add the capacitor. So that is for that. So you can use that any value, but in make sure it is in the nanofarad range. That is it. It is up to you.
Yeah, but see, whatever has been provided in the kit, we have to use that and we cannot measure. So I hope it's in the nanofarad range, and we
It
will
is
assume.
it is given, right? uh, the list of the components and what are the values of them of these components, it is
In the
given to
kit.
you, right? Kit.
No, in the kit it is not mentioned.
Okay, so that I can maybe confirm from Victoria and let you know. or Victoria will let you know that what are the values of the, because I also don't know whether it is 1 nanofarad, 100 nanofarad. Okay.
Okay.
Okay, fine.
Second thing is when we connect the 2.5 volts, we give the AC and DC together, like in OA part 1, step 6.
Hmm.
So we have to connect both the sources in parallel.
No, no, no.
Sorry, in series.
That is also there, but what you can do is directly you can give it AC, right? AC, and put that 1.5 sine omega, means there, if you go to pixel pulse, there will be one minimum point and the maximum point, right? When you
Hmm.
give sinusoidal
Hmm.
excitation, right? So you can add that, right? In 2.5, the AC signal will add, right? So you can use 1.5 and 3.5 and frequency, whatever you are giving. I think it is mentioned here. What frequency?
So this 2.5 plus 1 sine omega t,
Is
can
it?
we just
Yeah.
can we just not give a sine wave from pixel pulse,
Yes.
and then also give the 2.5 which is in ADLAM, and
Means
connect
you're,
both of them in series?
yeah, that is also possible. That will not be a, both of them. It will come as series. That is also possible. The easiest way out is directly giving a sinusoidal wave and just putting that 1.5 and 3.5.
Okay.
The minimum point, if you add a sinusoid to a 2.5 DC, so it will be 1.5, the lowest point, and the maximum point is 3.5, right? 1 it will add and subtract, so like that.
I'm not getting in pixel pulse where to give that how to move the
Okay,
sine wave up and down.
okay,
Oh, okay,
I'll
it's zero. Okay, 0 and 2.5 volts is mentioned along with the
ha ha
frequency.
ha. So
So
there
there
you
will
can
be.
change, no,
Okay, okay,
one minimum point and maximum point. I think you just have to figure it out how to
got it.
work it.
Okay.
Okay. Acha, one more thing in Pixel Pulse, you have to go to the settings, okay? Whoever is following,
Yeah,
so go to the settings, there will be one repeated sweep, okay?
yeah,
So if it is, I think you have to disable that. If it is enabled, you have to disable that.
yeah.
Okay, otherwise there will be a problem. Well, you will see that this is giving the output. It will show, but in reality it will not, when you connect to a oscilloscope, the actual output from your ADLM kit will not be this a correct one. There will be some discontinuous part. Okay, so please disable that repeated sweep if it is there in your, when you open that Pixel Pulse app. Okay, otherwise,
Ma'am,
yeah.
can you demonstrate an example of this AC excitation through pixel?
What? One
Ma'am,
example, AC
uh,
excitation example, right?
yes, ma'am. Can you
Okay,
demonstrate?
okay. I'll just try to open that. Just a minute. Just give me a second. I'll share the screen. Just a second. So you can see the pixel pulse software, right? So here you have to disable, it was enabled before, you have to disable that. Then you have to,
Ma'am, if you right click, then it'll work fine.
okay, thank you. Actually, it is not opening. You try. Yeah, so you have to give sign, right, as a source voltage. This is, so this will be what, 1.5 volt. This will be 2.5 volts, 1 kilohertz. This will be the, okay, like that. Are you able to see? This is 2.5. Like that. Okay. Understood? Like
Yes,
that
ma'am.
you can, you, and while channel B will be measure the voltage. You will measure the voltage. You can use channel B as an oscilloscope and it will measure the voltage. Okay. Now here you are, this is a source voltage, okay, source voltage or measure current, like that, source current, this is giving a voltage, right, source voltage, and 1.5, that is 2.5 plus 1 sine omega t, that will be the signal. Okay, whoever has asked this question, can you follow, could you follow this?
Yes, ma'am.
Okay, thank you.
Thank you.
I'll stop sharing. Yeah, so any other questions you have? Part 2, just a second. Please explain. Part 2, we are adding 1 kilohertz, which is large compared to 1.
Ma'am, here in this case, the voltage will be 1.5 voltage plus AC voltage, na ma'am, because it started from 1.5 volt, na ma'am.
No. This is from 2.5 plus 1 sine omega t, right?
Okay, that means we take the difference na for DC voltage, na ma'am.
Yeah, means it will,
Difference.
difference means add one, it will add and it will subtract, right? When AC and DC will
Okay.
add, right? Like that. That you can make it a same different source, and other means you can use that AC DC separately and make it series, that also will work. And
Okay, ma'am.
in part 2 we are adding one. So see this, when you add one, I think Kaushik Shankar has asked one question. In part 2, we are adding 1 kilo resistor in series with 10K, which is large as compared to 1K. It doesn't make much difference in balance, so the VAB remains 0. So should I mention this in video and continue to part 3? So this is the, in any case this is a not balanced condition for Western bridge. So why we are going for a Western bridge? Okay, to measure that small change in resistance, that small change will correspond to the VAB. Otherwise, if it is properly balanced, then what it will be, that VAB equals to 0. Otherwise, why to go for a Wheatstone bridge? We can always measure with a multimeter, or and directly measure. So in a multimeter, if say 100K you want to measure and plus 1K change we are adding. So in the, if the multimeter has a accuracy of 1%, so that will the if with that multimeter, if I want to measure 100K plus 1K, that will not make the change will be very, it will not show, and actually it will be erroneous output. Okay, but here what we are doing, if you are using a bridge circuit, that the small change in the resistance will be reflected as a voltage, that VAV small voltage will be reflected in the node voltages. That VAV, there will be not in the same, VA and VB will not be same. So that small difference will refer to that small change in change of 1K in the resistance. That's why you're using. So VAB will never be zero. It will show some value that it may be in the
Yes, ma'am.
millivolt. So that
Disabled range.
so that you have to inform, and what is the reason of using. The reason what I've said, maybe more clearer version, read through it, and why the bridge circuit is used. So Wheatstone bridge is not used just to connect two four resistances like that and just have a Wheatstone bridge. No, what is the main purpose of using a Wheatstone bridge? That also, that you need to understand. That 1K, if you are connecting with 100K, how it will be reflected in the VAB, and why is it reflected in the VAB, and what is the purpose of it. Okay, so that you have to understand. It will never be zero. Some millivolt voltage will be shown. So that is referring to what, why that millivolt change is coming. So that you have to infer in your video. Any more questions?
Ma'am, could you hear me?
Yes.
Ma'am, I have one question. Suppose the length of the video should be within 5 minutes, right?
Is it given to you as an instruction? Length of the video should be 5 minutes.
Yeah, I suppose it is given. It was
Ma'am,
previously
instruction
given for
is
the first
changed.
class.
Is it is mentioned in the
Now
first?
extended, but now extended to
Extended,
7 to 10.
extended. Yeah. 7 to 10 minutes.
Yeah, because this experiment whole in 5 minutes, it will be difficult, I think.
That is the thing. If it happens to be that suppose my video is getting to 11 or 12 minutes, so will it be okay? Suppose I'll have to explain each and every step. I think it will take more time. Suppose if I exceed the limit by 1 or 2 minutes, will it be a problem?
Yeah,
That is the
I
question.
don't think it will be a problem. I don't
Suppose
think
we
it will
have to
be.
explain each and every connections, right? In each of the steps.
Yeah.
So that will take a little bit time. So I think it will take some more time. So it will not be an issue, right? If I exceed the time
I
limit by
don't
one or
think
2 minutes.
it will be an issue. Just check whether you are able to upload the video. That's it. But don't make it a 15 minutes, 20 minutes video. That will be a difficult job for us. Okay.
And one more
Otherwise,
thing,
yeah.
yeah, ma'am.
No.
For each and every part, we'll have to separately explain the connections and then go on with the results, or is it okay that if we directly show that we have made the connections? I mean, I'm asking that we'll have to show the steps while I'm making the connections, or I'll have to show the ready circuit and then I'll explain the values that I've got.
So first of all, as I have said, first of all, you have to show that these are the you have to show the multimeter value, like when you measure the resistance values. What is the multimeter value? Values you have to show. Okay, just not saying it loud in the video and just showing it on the sheet. That will not do. You have to show practically that this is the multimeter value in the multimeter when you measure a voltage. That this is the value showing in the multimeter. Okay. So that thing,
Okay.
it needs to be clear. Otherwise, we don't know whether you have conducted the experiment or not. Okay. So that
Okay.
thing should be clear, and you can not every time doing the maybe you are changing R1 with 1K 100K. It was in the part 2 you have changed with 1K, for example. So that you will just say that I have changed that with 1K, and then continue the experiment. That's it. Okay, but you have to
Okay. That
particularly
means
but you have to
the step
particularly
by
yeah, step by step should be there. You have to particularly show that this is the node 1 node A voltage. Show the
okay.
show the multimeter value. Node B voltage. What is VAB? What is it showing? What in which range you have used the multimeter? 20 millivolt, 20 volt, 1 volt, like that. So there are some range, right? So that you have to show. And what if there is any differences, that you have to mention. Okay.
Okay. Okay. Thank you.
Thank you. Any more query?
Ma'am, I
Yes.
receive only 100 kilo ohm resistor. Should I use the 200 kilo ohm resistor, or should I add some more resistor and create 100 kilo ohm resistor and perform experiment?
Okay, you have checked properly that you have got
Yeah,
got
ma'am. I check.
okay.
I check every register and everything.
So
Only I have only
what all
two
the what all resistance values you have received?
uh, around 98 and
No,
98 kilo ohm.
no. I'm just saying 200K you have got. Other values, other registers.
Ma'am, I have only two 100 k 100 kilo ohm resistor, and the other is different values.
Other is what value? 1K you have, as mentioned.
I have 1K.
1K, then 10K you have,
10K.
right?
I have 10K also, and I have 1K also, and I have 200 plus K. Mine around 219K, 220K.
So 220K, how many you have?
I think around 15.
15 registers you got 200 values.
Yeah.
Okay, maybe in the first part you can do is R1, R2, R3, R4 should be similar. So you can use 200K and C. That's it. Okay.
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 And then after that, in the last part of part one,
Yeah.
that you can continue with 1K, 100K, and 210K. Like other part of the experiment, you can continue, right? Like that,
Okay.
no? Yeah.
Okay.
That's it.
Thank you, ma'am.
Just mention it in the video that
Yeah.
this is
Yeah.
the case,
Yeah,
okay?
ma'am.
So that
Okay,
while
ma'am.
checking, we can be sure about it. Okay. That's
Okay,
it.
ma'am.
Anybody, any more questions?
Ma'am,
Yes.
ma'am, for part 2 of the experiment, do we need to use both 2.5 volt DC and that AC voltage, or just DC is enough?
No, both.
Okay.
Ma'am, I have a question. What is corner frequency?
That you read it out by
Yes,
yourself.
ma'am.
Then only you'll understand the whole thing. Okay. Corner frequency, what is the use of that? Any more questions? Anyone have any more doubts? Any questions?
Ma'am, one more
Yes.
thing.
Yes.
Suppose I'm seeing one point in the part 3, point number 7. It is
Yes.
written that represent the circuit using the Thevenin equivalent circuit across the nodes. Right. That means it is the circuit without the capacitor, right?
Yes. Correct.
Without the capacitor, only the resistances and the source that I'll have to
Yeah.
represent in Thevenin
Thevenin
equivalent,
equivalent.
right?
Yes. Correct. Yes.
And the capacitor will be acting as the load to the Thevenin equivalent.
Correct. Yes.
Okay, ma'am.
Yes, Dhruv.
Ma'am,
Yes.
ma'am, in this AC voltage, we have to give 2.5 volts plus 1 sine omega t. So we
Yes.
will take base as 2.5 and peak as 3.5.
Peak is base is 1.5, no? One sine omega t. One is the amplitude of that v peak of that sine wave, right? So
No, but
one,
it is 2.5 plus 1 sine omega t.
so it will be what? One is a v peak. So it will be down also, no? Minus also 2.5 minus 1, that the lowest base, and the above will be 2.5 plus 1. No?
Okay, so 1 is the base value and then 2.5. Okay.
1 is the V peak voltage. Okay. V peak.
Okay.
Maximum value, right?
Yes.
So that will be subtracted and added, right? On both on that will add to 2.5. So it will be 1.5 and 3.5.
Okay.
Any more questions? Any more questions you have? Anybody?
Ma'am, Keystone Bridge is specially for resistance measurement, na ma'am?
Yes.
So, what is the difference between this measurement of resistance by Keystone Bridge and by multimeter, ma'am? Could you please explain, ma'am?
I didn't get you.
Ma'am, what is the difference? Because with multimeter, we are able to measure resistance, and Keystone Bridge also used for resistance measurement, ma'am. So, what is the difference, ma'am?
Yeah, so in multimeter, if you measure the resistance, let's say 100K, you can measure, you are measuring, giving us 100K. Now, when you add, there is a small variation in the resistance value, okay? Like you add 1K, like for example, that I already answered, I think, asked by Koshik Shankar. So in that case, multimeter has an accuracy of 1%, let's say, okay? So it will be, if it is measuring 100, it will be either 1% accuracy means either it will be 101 it will measure or 199 it will measure. So already the multimeter has 1%. So if there is 1K variation in the resistance, so that variation you cannot say directly that is it the variation in the multimeter, or it cannot measure the resistance variation accurately, no? You cannot say that that value, if you are reading, is erroneous, right? You got my point?
Yes, ma'am. Yes, ma'am.
So, but when you connect that resistance value, if in the Wheatstone bridge, let's say R1, now it is changing from 100 to 1K, 100 plus 1K, that 1K change corresponds to the VAB. Before it was VAB was 0, right? In the balanced condition. Now the change will only correspond to the output, not the whole. It will not, that 100K will not correspond to VAB. Only the change in the resistance will correspond to the VAB. That will be more accurate now. Now you are able to use the full range now, right? Before it was what, the whole 100K plus 1K. Got my point?
Yes, ma'am.
Maybe you can read it out more, then you will be more clear. This is the like some basic, okay? So on that point you can read more and you will understand, okay, what is the need of Wheatstone bridge. Any more questions you have? uh, so nobody has any questions? Everyone has conducted part 3, conducted the experiment in part 3. That I don't think now any results will be published. That you can ask Victoria. I don't know about that, whether any results will be published. Any more questions? Shall we wrap up the meeting? We will wait for 2 more minutes and then we will wrap up the meeting. Please let me know if you have any questions. I'll wait for two more minutes. Yes, I think Kaushik Shankar has raised one valid question. Kaushik? Yeah. So he said that the ADLM kit has only one, there is no separate ground like in traditional. So the ADLM kit has only one ground. So if we are using it for excitation, we cannot measure the VAV. It rather measures the voltage of node A or node B. What should I do? So yes, in this, if I think many of you have not done the part 3, that's why nobody asked this question. So that's why I didn't give a proper this thing. So I wanted you guys to do the experiment and understand it, and then you can not understand that, realize the issue. So you cannot measure VAV uh, in the through your oscilloscope, that ADLM kit. So that is a problematic. So either you have to measure VA and VB. So VAV will not be measurable. Is not measured. Cannot be measured. So better you have to. Why? Because you cannot do that VA and VB separately and then subtract. That also you cannot do, because you have to simultaneously measure in at one instance, simultaneously measure VA and VB, and then only you can subtract. That you cannot do, because you have only channel 1, channel B. Channel A is you are using for excitation, and channel B you are using as a to measure. So simultaneously you cannot measure VA and VB. So that will be a issue. So, but you need to understand that you can do, what you can do is continue from part 7, from realize the Thevenin equivalent circuit for the Wheatstone bridge circuit, and then connect a capacitor in the load of that circuit and find the frequency. Yes, Kaushik, I'm answering your question. Yeah. So, and separately you can you can just do the Thevenin equivalent circuit, connect the capacitor and see the changes in the VAB when you change the frequency. When you switch the frequency from 1 hertz to 1 kilohertz as written in the document. So that you can do. So that is it. So that is a brief, but one you try doing that and try to figure out why is it not possible. And as because Kaushik has already uh, mentioned, but you also should understand and realize by doing it by yourself that why is it not possible, and then you can explain it in your video, and then continue from 7.7 of your part 3. So that is it. Okay. Any more questions you have? So one thing, Victoria, are you there in the chat? Okay, fine. So any more doubts you have? Please let me know if any more doubts you have. Shall we wrap up the meeting?
ఆన్ చేయదండి అది ఆన్ చేసింది
Victoria,
నాకే వినిపిస్తుంది నీకు వినిపించలేదే
whoever's mic is unmute, can you mute your mic, please? So if anybody have any questions, you can ask or you can leave the chat. Okay, so we'll wrap up then. If nobody has any question, you can leave the chat. We'll wrap up.
Thank you, ma'am. Thank you.
Thank you. So everyone can leave the chat, leave the meeting. If you have any doubts, you can ask, or else you can leave the meeting. Everyone can leave the meeting.